Let's start by understanding Turing machines. We have studied finite automaton, uh, which includes DFA, NFA, and PDA. Now, Turing machines are our most powerful models of computers. You can think of them as finite automata with an infinite tape for storage. If we look inside a Turing machine, which is a hypothetical concept, so it needs to have three different components. The first component is an infinite tape which is divided into discrete cells. So imagine a long tape, and that tape is divided into cells. Each cell can contain one symbol. A Turing machine must also have a device or a mechanism which allows access to one cell at a given time. This device or mechanism is called a head. A head can read from and write to the tape, but only at the location that it's pointing right now. The head can also move to the left or to the right, or it can stay there. The third thing that is there in a Turing machine is its memory. Memory is there to ensure we have a location to save the current state from a given fixed finite number of states. Next, let's discuss the Turing machine's tape. So, what is the tape? The tape is a device on which we're able to write some symbols and then read them back. The tape is infinite in the sense that it stretches to infinity in both directions. So, if you want to move to the left any number of times, the Turing machine is not going to stop us. Likewise, if we want to move to the right any number of times, the Turing machine is not going to stop us or tell us that it is out of memory. When we want to write inside the Turing machine, we have to give a notation or a symbol to an empty or a blank cell. In this case, we can use a symbol such as delta or any other symbol in case of J flap. So the input starts on the tape. It is surrounded by delta with the head at the leftmost symbol. So if the input is epsilon or empty string, then the tape is empty and head points to an empty cell. So if you look at this diagram, you can see that there's a tape, there is a string, and the string is surrounded by deltas, and there is a control which essentially discusses how exactly the head will move next. The next thing to talk about in a Turing machine is a program. You can consider the program as a transition function. So essentially, we look at the tape, whatever is under the head, and the current state of the Turing machine, and based on that, we either write a symbol, we move to the left or to the right, or stay in place, and it can also update the state which is inside the memory. In terms of definitions, A Turing machine language is a set of strings that it is able to accept. Similar to the push-down automaton, once a Turing machine enters an accept state, it stops. And if something happens abnormally, then there is simply no transition. Turing machines are represented by diagrams. Diagrams are represented in different ways in the Goddard book or the Sipser book. In the Goddard book, the Turing machine is represented in the form of an arrow labeled with a triple. So it's similar to the finite automaton. The only difference is the arrow is labeled with a triple. Why? Because it has to tell us two things: the change in the symbols, and the second thing is the move direction. The change in symbols is represented by the old symbol, followed by the new symbol, and followed by the move direction. Move direction can be L if it moves one cell to the left, or if it moves one cell to the right, and S, that means stay in place. So if I were to look at a triple 0, 1, L, that would mean the old symbol, which was red, that would be 0. And now I have to write a 1 in the same cell, and subsequently I'll move the head to the left.